All right, here we go. Let's hope that this 2.8 works. Okay, so 2.8 here. So last time, I guess in 2.7, we covered functions. And so here in 2.8, we are going to cover a type of function called one-to-one functions, and we're going to take a look at their inverses. Okay. So here, we're going to get a little theoretical here only because, so what happens is there's a study of abstract algebra in higher mathematics, and they look at, I guess you can say they look at the structures of things, and one of the things that's required to be part of something is having an inverse. And then later on, these topics in abstract algebra carry over into physics and computer sciences. Okay. All right, so first of all, we are going to take a look at a one-to-one function. And the reason why we're looking at one-to-one functions is because not all functions have inverses. And it turns out that the functions that do have inverses are one-to-one functions. Okay, so a function such that every element in a set A maps distinctly, and that's the key word right there, to an element in set B. Okay, so it sounds very similar to the definition of a function. A function says, okay, it's a relation such that every element in A maps to an element in B. Okay, but we saw that for functions that two different x values can actually get mapped to the same y value, okay? And it would still be a function. So here, it would still be a function, but it would not be a one-to-one function. So what this is saying is that in order for it to be a function and also a one-to-one function, is that the x values need to get mapped to completely different y values. They cannot get mapped to the same y value. Okay. So here's a visual. So suppose that I have my domain here, x1, x2, x3. And here's my set B. So this here would be an example of a function that is just a function, but not one-to-one. I'll show you. So I'm going to use that notation there, 1-1, to mean one-to-one. Okay, so here, if every x value gets mapped to a y value, and it doesn't matter which one, then it's a function. So x1 gets mapped, great. It only gets mapped to one y value. That gets mapped, great. And this one gets mapped. So every x value gets mapped to one y value. That's the requirement for a function. Okay, this is what it looks like if it's going to be a one-to-one function. So here, if I have these, then every x value has to get mapped to its very own y value. So maybe x1 goes here and x2 goes up here, Well, x3 can only go over here, okay, because the other y values are taken, okay? So this is what it means to be a one-to-one function. And yes, I could have used the 1-1. Okay. In case you're not sure what that notation is. Okay. All right. So if you recall in the last section, I think it was, when we first introduced functions, we said, okay, well, if you're given a graph, here's one way you can tell if it's a function. You can use the vertical line test. Okay. Well, we have the horizontal line test to test whether or not the graph of a function is one-to-one. Okay, so we can use the horizontal line test for one-to-one. Okay, so let's take a look at a few examples here. All right, so we're going to take a look at the line. And remember, it has to be a function first, okay? And we will take a look at a parabola, open upward. Okay, we'll take a look at x cubed graph. Okay, and we'll also take a look at absolute value graph. And we will take a look at sideways parabola. And we will take a look at these here, which we will cover more in the last section of chapter 3. Okay, so let's take a look at these 6 graphs. Okay, let's start with letter A. Okay, so first of all, does it pass the vertical line test? Yes, it does. So it is a function. Okay, so does it pass the horizontal line test? Yes, it does. So it's a function and it's one-to-one. Okay. Here, let me get my pen out. Okay, so what about letter B? Is it a function? Does it pass the vertical line test? Yes. Okay. Does it pass the horizontal line test? Well, no, it doesn't. So it's a function, but it's not a one-to-one function because right here, it crosses the graph, horizontal line crosses the graph in 2 places. So this here is a function, but not one-to-one. Okay. All right. And letter C, is this a function? Yes, it is. It passes the vertical line test. Is it a one-to-one function? Does it pass the horizontal line test? Yes, it is. Okay. So this is yes. It's one-to-one. Okay, let's take a look at letter D. Does it pass the vertical line test? Yes. Okay, so it is a function. The question is it a one-to-one function? Does it pass the horizontal line test? Nope. It crosses 2 places here. So it's a function, but it's not one-to-one. Okay, and then let's take a look at E. Does it pass the vertical line test? No. Okay, so it doesn't cross It doesn't pass the vertical line test because it crosses in these two places right here. So E is not even a function, so we don't even have to check if it's a one-to-one function because, well, it's not even a function. Okay. Okay, and then letter F, does it pass the vertical line test? Yes, it does. Does it pass the horizontal line test? Yes, it does. Even though it looks like it's not, uh, they do tend towards the axes. So little by little, it's getting closer and closer to the axes. Okay. Now, so let's take a look. Letter B and D are functions, but they are not one-to-one functions. However, there is a way where if you restrict the domain, let's say we're looking at letter B. Okay, we have that parabola. So that's the graph of y equals x squared. Okay, so if we restrict the domain, because right now the domain's all real numbers, right? But if we restrict the domain and we say that we only want the positive x values to be used, okay? If we do that, then we end up with just half of the parabola, okay? So we end up with just the right half of the parabola, and in which case now it passes the vertical line test, it passes the horizontal line test. So in this case, by restricting the domain to x values that are greater than or equal to 0, okay, then we do have a one-to-one function, okay? All right, so just look for those in the homework problems if they say, oh, is this a function, a one-to-one function? Well, if they restrict the domain on this parabola, then yes. Okay, same thing with this absolute value. If we restrict the domain to x values greater than 0, yes. If we even restrict it to x values just less than or equal to 0, then it would also be a yes. Okay, so if we just restrict the domain somehow so that it passes the horizontal line test, then we're good. Okay, so like I was saying earlier, not all functions have inverses. So only functions that are one-to-one have inverses. So let's talk about inverse functions. Okay, so let's let f be a one-to-one function with domain A and range B. Then its inverse function and we use this notation f, and it's not that it's an exponent, it's a symbol. Okay, so f negative 1. Okay, that's the notation we use for inverse function. So f is a function with domain A, range B. So the inverse function has domain B and range A. Oops, sorry. We're supposed to switch that. Got all excited about making the emphasis. Okay, so what this is basically saying is that the x and y values actually switch, okay? And you'll see this idea come up when we talk about finding inverses. Okay. All right. So let's take a look at a few examples here. We'll take a look at an example where we have a table of values. We'll take a look at another example where we look at functions that are being evaluated. And then we'll take a look at an example with their graphs. Okay, suppose that this is my function f of x, and it's made up of this table of values, 0, 1, 1, 2, 2, 3. Okay, so there's my function, and there are some points on my function. Okay, then my inverse function, according to the above definition, is going to be made up of these values, okay, where the x and y's switch. So here, now the y value from the f of x is now going to be an x value. See how they switch? And then the 1, 2 in the f of x chart will be switched. So it's 2, 1. And the 2, 3 values under the f of x chart will now be 3, 2. Okay, so whatever you have for your x values in f of x, they become your y values for the inverse. Okay. Suppose that you have these values. Suppose that in your regular function, when you plug in 4, you get 12. When you plug in 5, you get 15. When you plug in 6, you get 18. Okay, suppose those are the values you get when you use your regular function. Then for your inverse function, for your inverse function, if you plug in 12, you should get 4. And if you plug in 15, you should get 5. And if you plug in 18, you should get 6. Again, the x and y values switch places with the inverse function. Okay. And the same thing will happen here if you're given a graph. Okay. Let's suppose that these are, suppose that we have these points for your f of x. Okay, suppose that we have, here, I'm going to go ahead and put some tick marks here. Okay, suppose that your function f of x is made up of these points, -1, -4. Here, I'll write them down. So -1, -4, 0, -2, 1, 0, 2, 2. Okay, and suppose that I have this line. It's supposed to be a line. Crooked line. Okay, so if this is f of x, then over here, when you graph the inverse, again, for the inverse, your x and y's are going to switch. So instead of having over here, we have -1, -4, they're going to switch. So we're going to have -4, -1. Okay, so -4, -1. Okay. And then instead of 0, -2 over here. So instead of 0, -2, we're going to have -2, 0. Okay. And then over here for f of x, we have 1, 0. So then for our inverse, we should have 0, 1. Okay. And then here we have 2, 2. And if we switch that around, we will still get 2, 2. Okay. So we end up with this line for the inverse graph. Okay. Okay. So let's take a look at this next property about inverse functions. Okay, so inverse function property. And this is going to be the property that you use when you see a problem on the test or on the homework where they say show or verify that these two functions are inverses of each other. Okay, so you're going to be using this property here. All right, let's let f and g be one-to-one functions. Being one-to-one means you have an inverse, okay? With domains A and B. Okay. So then it turns out that F and G are inverses of each other. If and only if, I'm just going to use this symbol here, IFF. So that means if and only if. Okay, so if and only if. In math, that just means that it's a biconditional. It goes both directions. F and G are inverses of each other if the following are true. You can say it the other direction. The following are true if F and G are inverses of each other. Okay, but that's just a technicality. Okay, so F and G are inverses of each other if and only if. Number one, remember composite functions? Okay, so if you take the composite functions f circle g of x, and you take the composite function g circle f of x, it turns out that you should get the same answer. When you do these composite functions, you should get the same answer for both if they are inverses of each other. It turns out if you do that top, the f circle g composite, and if you do the G circle F composite, you're going to get the same answer. Both of them will give you the value X. Okay. So when you see a problem where it asks you to show that F and G are inverses of each other, what you need to do is show that both of these composites equal X. If you can show that both of the composites equals X, then you have verified that F and G are inverses of each other. All right, so use this when asked I don't know how to emphasize this because it gets missed a lot on the test. So I use this when asked to show or verify two functions are inverses of each other. Okay. And I'll do an example next. Okay, so let's go ahead and show that F and G are inverses of each other. Okay, so suppose I have this for my F function, x minus 6, and suppose my G function is x plus 6. Okay, so again, to show that F and G are inverses of each other, we need to show that the composites, both of them, F circle G and G circle F, we need to show that both of them equals X. Okay, all right, so let's do the first part. F circle G. Okay, so we are doing F and plugging in G. Okay, and that means we are plugging in what's G. G is x plus 6. Okay, so we're taking x plus 6 and plugging that into the F function. So right up here, right there, I am going to replace that x with x plus 6. And then minus 6. And removing the parentheses, I get x plus 6 minus 6, which gives me x. So I did the first part. I showed that F circle G does equal x. Now I need to do the second part. I need to show that G circle F also equals x. Okay, so G circle F means G of F. Okay, and G of F means G of x minus 6. So that means I have to replace all the x in the G function with x minus 6. So this right here gets replaced with x minus 6. So x minus 6 and then the plus 6. Remove the parentheses and I get x minus 6 plus 6 and I get x. Okay, so I showed that F circle G equals F circle G equals x, which is the same as G circle F. Therefore, this is the symbol, the math symbol for therefore, these three little dots. Therefore, F and G are inverses of each other. This is our conclusion. Okay. Okay. I'm going to have you guys try this one. So try this. This is going to be your f function. F of x equals 2x minus 5. And your g function will be x plus 5 over 2. Okay, so go ahead and verify that these two functions are inverses of each other. Do exactly what I just did. Show that f circle g equals x and show that g circle f equals x. Okay, so go ahead and hit the pause button, and when you're done, come back to see if you get the same answer as I do. What am I doing here? Hold on a second. Going too fast. Come on, eraser. Okay, here we go. Okay, so that's how you would work those out, showing that both composite functions equal x. All right, let's see what else we have here. Okay, finding inverses. Okay, that's how you verify. So now let's take a look at how you actually find inverses. And this is why people miss that question that you just did, because this next part becomes the focus. And so they start using this next part to verify two functions are inverses. Okay, but don't do that. Okay. All right, so finding inverses. So we're using that idea of that definition of inverses, how the domain arranges switch. So the x and y switch, right? So when we find them, that's exactly what we're going to do. So you're going to be given a function, a one-to-one function, and then it's going to say, well, find this function's inverse. And what you're going to do is you're going to switch the x and y. Okay, so that's going to be the first thing you do. And remember, the symbol f of x, that's your y. Okay. And then what you end up doing is solving for the y. And the result turns out to be your inverse function. Okay, so let's have a look here. I need some space. Waiting for it to scroll up. It's lagging. Okay, let's bring that back. Okay. All right, so let's take a look at this example here. Let's find the inverse function if f of x equals 3x minus 2. Okay. All right, so again, that symbol, that function symbol f of x, that's your y value. Okay, so let's go ahead and rewrite that using y instead of f of x. Okay, so that's your y value. Okay, so we haven't done step 1 yet. Okay, so it says here for the first part that we switch the x and y. Okay, so let's go ahead and do that. And I'll actually do it with red here. So I'll put the x here. And I'll put the y over here. Okay. Okay, so here we go. All we did was switch the x and y, and now we can go ahead and solve for y. Okay, so add 2 to both sides. So I get x plus 2 equals 3y. Divide by 3, both sides. Okay, and so we get x plus 2 all over 3 equals y. So that right there, that's your result. So that's your inverse function. Your inverse function is going to be x plus 2 all over 3. Okay. All right, so that is pretty much it for 2.8. That's functions and their inverses. Okay, so sorry about that other video not having sound. I checked all the other ones and they should be good to go. All right, so keep up with your homework. Email me, message me if you have any questions.